All right, we're going to try and solve this problem. dy dx is equal to y natural log y over 1 plus x squared. And we're given the initial condition that y of 0 is equal to e to the second power. Okay, so you'll notice that this is, at first glance, maybe not quite separable, but we notice that all of the x terms are downstairs, all the y terms are upstairs. So we can simply want to think about cross multiplying or moving the dx over here and moving this term down there. So you get dy is equal to y natural log of y is equal to dx over 1 plus x squared. Okay, so now you notice that we have all the x's on one side and all the y's on the other side. Now to integrate this on both sides, as we noticed in class, the natural log of y has, if we take the derivative over 1 over y, so this is screaming for a u sub. So if you notice that if we let u equal the natural log of y, then du is going to equal dy over y. And notice dy over y, oh, that's just du. And this is the natural log of y is the u term. So this side simplifies quite nicely to just being the integrand would be du over u. Okay, so that's the left-hand side. And then over here on the right-hand side, this is going to require a calculation that we haven't encountered quite yet in class. So this is just going to have to take it on faith for the moment, but we're going to let x equal tangent of theta, where theta is an angle. Okay, and then dx, if you recall, is the derivative of tangent is secant squared theta, d theta. And the reason why we're doing this is because if you remember, the cosine squared theta plus sine squared theta is equal to 1. Okay, this relationship is called the Pythagorean identity for trig functions. So if you divide everything through by cosine squared theta, like so, you get this is going to equal 1 plus sine squared over cosine squared. Well, that's tangent squared theta, and that's going to equal secant squared theta. So this part looks very similar to this part once we make this substitution. Okay, so if we do that, we put in x equals tangent theta, you're going to get tangent squared theta out, and then the dx becomes this whole thing over here. So this becomes equal to secant squared theta d theta divided by 1 plus tangent squared theta. And just like you noticed over here, 1 plus tangent squared theta is secant squared theta. So actually this ratio is secant squared theta d theta over secant squared theta, and those reduce to 1. So this is actually just the integral of d theta. So this really complicated integral on this side, and this reasonably complicated one on this side simplify quite nicely to just du over u equals d theta. Okay, and now if we want to compute the integral of both sides, we can do that. And so the integral of du over u is the natural log of u. I am being liberal with my application of the absolute values, so be careful of that. And then over here we have theta plus a constant. Okay, now remember, we made the substitution up here that log of u is equal to, back up here, that u is equal to the log of y. So we're going to come back and start back substituting in. And so first of all, I'm going to take the exponent of both of those because these are inverse functions, and that will produce then u is equal to e to the theta plus c, which is e to the theta e to the c, where I've used the fact that e to the a plus b is equal to e to the a times e to the b. So that's what I'm using here. You can add exponents. It's the same thing as when you multiply like bases. Okay, a little off there. Okay, so now that we have this combination, I can relabel this as another constant. I usually call it in capital A. So we have u is equal to a e to the theta. Now we know that u was actually back up here equal to the natural log of y. Okay, so to simplify this a little bit more, we have the natural log of y is equal to a e to the theta. Okay, and so to solve this part a little bit more. Okay, to solve this part a little bit more, we want to get rid of undo the natural log. So in order to do that, we're going to have to exponentiate everything one more time. So we have y of x is now written as e to the a e to the theta. So we'll have to look at how to get rid of that theta, going back up to our substitution up here, okay, before we can plug in for our initial condition. So okay, so we had y of x is equal to, back up here, we have y of x is equal to e to the a, e to the theta, and we had that y of 0 is equal to e squared. Okay, we also had that, we said that x was equal to tangent of theta. That was our original substitution. So if we move backwards, we're going to take the tangent inverse of both of these functions, and so theta is equal to tangent inverse of x, which is also sometimes written as arctan of x, depending. And this inverse here, this is not an exponent, it's a notation that means arctangent, or the inverse of tangent. Okay. All right, so let's plug this back in. So we have y of x is equal to e to the tangent inverse of x. Okay. So let's plug this in and see what we get. So y of 0 is equal to e squared, which is equal to e to the tangent inverse of 0. Oh, okay, so I think we're done. Okay, so on this one, the tangent inverse of 0 is 0, so we have e to the a, and then e to the 0, so this goes to 1. Okay, and so then looking at the exponents, okay, since the bases are the same, that gives us then, this implies that a is equal to 2. Okay. So since this term is 1, then we can just equate the exponents, and so a is equal to 2. So finally we get y of x is equal to e to the 2 e to the tangent inverse of x. Okay, and so that's our final result.